differential equations that are of this type are called homogeneous differential equations, and this can be solved by making a substitution, and then what happens is when you make that substitution, the homogeneous differential equation is transformed into a separate one. And I'll show you how this happens through an example. So example 1, use substitution y is equal to vx, where v is a function of x, to solve this differential equation. So there are a few tricks that I want to show you here. And this is basically one of the things that you can do that can help you to solve this. Multiply both the numerator and denominator by 1 over x to the power n, where n is the sum of the powers of x and y in each term, or n is the highest degree of x, the highest degree of the variables in each term. For example, here the highest degree of x is 1, and the highest degree of this term, of the variables in this term, is 1. So the highest degree of y is 1 definitely, and here is 1. So what you're going is we'll multiply the numerator and denominator by 1 over x to the power 1 and 1 over x to the power 1. Okay, so we multiply both numerator and denominator by that. So let me just write it down to give you an idea of what I've just said. So multiply both numerator by 1 over x to the power n, where n is the sum of the powers Okay, so like I said, so what you're going to do here is we have our differential equation, dy over dx is equal to x plus 2, I don't know what's happening here, x plus 2y over x. And then what we are going to do is to multiply the numerator by, use a different color here, multiply the numerator by 1 over x, and multiply the denominator by 1 over x. And if you do that, what you'll end up with is this equation, dy over dx will be equal to 1 plus 2 into bracket y over x over 1. So there's no need of writing over. Yeah. So you just end up with this expression. 1 plus, let me write it properly. 1 plus 2 into bracket y over x. Okay. So already you can see here something that is familiar to what I mentioned previously. So what I'm going to do is I'll say let v, remember we are using this substitution here, so I'm just going to say let v be equal to y over x, if that makes sense. So let v is equals to y over x. So in place of v, I'm going to plug in y over x. And if you look at this equation, I have y over x here. So that means I'm going to plug in v. So what I'll end up with is dy over dx will be equal to 1 plus 2v. Now, so I'm just going to put that in a little box. We'll come back to that in a minute. But what I want to do is to move on to this side. Okay, now this is the same as if we let v to be equal to we know that y here is equals to vx, which means dy over dx here will be equal to, and if you use product rule, that will be equal to v d over dx of x plus x d over dx of v. So what we'll end up with is dy over dx will be equal to v plus x dv over dx. Now already what you can see here is this is an equation for dy over dx, and here we also have an equation for dy over dx. So what you're going to do is to equate these guys together. All right. So if we equate these guys together, what we'll end up with is v. So but basically we end up with v plus x dv over dx is equal to 1 plus 2v. Now this is a separable differential equation. All right, this is a separable differential equation, which means we can solve it by separating the variables. But anyway, let's go ahead and simplify it. What we'll end up with is x dv over dx will be equal to 1 plus v. So this is same as x dv, or we can just separate the variables in one step, and what we'll end up with is dv over 1 plus v is equals to dx over x, right? And then what we can do is just integrate this guy, and what we'll end up with is ln 1 plus v is equals to ln x plus c. I know I'm supposed to use absolute value, but I'm just going to ignore that and move on. So once I have that, remember what we said initially was that our v was equal to y over x. So maybe it's time that we can come back and plug that in. Let me just go back to the question. So the question is to solve that. All right. So at this stage, what we can do, let's simplify it a little bit further, make it look a little bit better before we can move on to make substitutions. So this can be written as ln 1 plus v is equal to ln x. Now what I'm going to do here is that is c. So how about instead of writing c, I wrote something like plus ln plus lna. All right, so it's the same thing, it's still a constant. All right, so instead of plus c, I'll just write lna, and the reason is I want to group these guys together. So what I will end up with is ln 1 plus v is equals to ln x, and I can put this together to end up with ln ax. That was the whole idea of writing in terms of logarithms. Anyway, so what I can do is I can cancel out the logarithms. So what I end up with is a simpler equation without logarithms. And now I can plug in. So in place of v, I can plug in y over x. So 1 plus y over x is equals to ax. And then I can go ahead and multiply both sides by x. So x plus y is equals to ax squared. And then I can go ahead and say, which means that y is equal to ax squared minus x. So this is a general solution, okay? General solution to that part. So this is just a general solution. So now we'll move on to part B, finding a particular solution at y is equals to 3 over 2 and x is equals to 3, which means we'll move on to part B. And so at y is equals to 3 over 2 and x is equals to 3, we can plug this in into this guy. So we can plug into this guy to find whatever the constant is. So we'll end up with 3 over 2 will be equal to a into 3 squared minus 3. So 3 over 2 is equals to 9a minus 3. And that will be equal to 3 over 2. So we'll end up with 3 over 2 plus 3 is equals to 9a. So that will be 9 over 2 is equals to 9a, which means that a will be equal to a half. So if a is equals to a half, it means that our equation will be y, therefore we have y will be equal to, now back to our general equation there. So a is a half, so a half x squared minus x.